Imagine this scenario. A neurosurgeon is deep into a really delicate spinal procedure. I mean, every single cut, every movement, it carries just immense risk.
Absolutely. High stakes.
And then suddenly on the monitor, a critical signal changes. Now, is that a surgical complication starting, or is it maybe just a shift in the anesthesia?
Right.
In that split second, knowing the difference can, well, it can literally mean avoiding permanent neurological damage for the patient. That's the kind of high stakes world we're diving into today. We're going to explore how medical teams get that immediate, often life-saving knowledge, and we'll focus on a really remarkable tool, the IMME Cumulation web application.
That's right. IMM, Intraoperative Neuromonitoring. Basically, it's like having constant vigilance over the patient's neurological function, their brain, spinal cord, nerves, all throughout the surgery.
It's a safety net.
It's the ultimate real-time safety net, yeah. And a core part of that involves looking at motor evoked potentials, or MEPs, and also cortical sensory responses. These signals, they give the surgical team instant feedback. It lets them adjust, maybe prevent complications before they become permanent. It's all about being proactive, not reactive.
Okay, so if IOM is this crucial safety net, how does a tool like this simulation actually train someone to use it effectively, to interpret those really critical signals?
Good question.
Yeah, so our mission in this deep dive is to unpack exactly how this high-fidelity simulation helps clinicians, helps technologists, students too, master that complex skill of interpreting the electrophysiological data. Specifically, how it trains their brains to recognize those significant changes that indicate, neurological risk. Okay, let's really unpack this simulation and what it means for learning. So what makes this simulation maybe revolutionary for training these neuromonitoring specialists isn't just the hands-on part, but it's the incredible realism, the high-fidelity aspect.
Right.
It's designed to give you a completely safe environment where you can build that crucial muscle memory for interpretation. You can make critical mistakes and actually learn from them, which, well, obviously is just impossible in a live OR.
Absolutely not.
You're right there sort of in the driver's seat of an active monitoring session, experiencing these realistic clinical events, and you have real-time control.
And what's fascinating here is just how much detail they've actually built into this. It makes it feel incredibly real. It's like looking at a full dashboard of vital signs, right? With the multi-channel montage showing all the different nerve pathways being monitored at the same time.
Okay.
So this means you're seeing responses from various points, including both peripheral muscle MEPs and those cortical EEG-like responses from the brain. And crucially, they've included things like signal jitter.
Ah, the noise.
Yeah, those tiny natural fluctuations you always see in real patient data, and also complex waveform morphologies, which just means, the various shapes and patterns these electrical signals can take. Without those sort of realistic imperfections, you wouldn't be truly prepared for the messy, unpredictable reality of the operating room.
So when you first fire up the simulator, the interface seems pretty clearly laid out. It looks like it's designed for, intuitive use.
Hmm.
On the left, you see the montage panel. That's basically a visual map, right? Showing where all the monitoring electrodes are placed on the body.
Correct, a little diagram.
Then in the center, there's this big waveform display where all that real-time electrical activity is pulsing across the screen. And then conveniently off to the side, you find the control and information panels. That's where you actually interact with it, manipulate the simulation. And for those times when you really need to focus in, maybe examine a subtle change, the channel selection feature seems, well, incredibly intuitive.
It is very straightforward.
You could just click on a specific channel's location right on that montage diagram, or even directly on its waveform trace in the main display. And that chosen channel immediately gets highlighted, making it easy to, identify and analyze without getting lost in all the other data streams. Okay, we've talked about the interface. But the real power, I think, where the learning truly comes alive, is its ability to throw those critical intraoperative curveballs at you.
Yeah, that's the core of it.
Here's where it gets really interesting. The ability to simulate critical intraoperative scenarios.
Absolutely. So one of the key simulations is the surgical event. You trigger that with the little save button.
The explosion button, right?
Yeah, exactly. This mimics a focal ischemic event. So essentially a localized interruption of blood flow to a specific nerve or maybe a brain area.
Okay.
Think of it like maybe the surgeon inadvertently presses on a nerve or perhaps a blood vessel gets compromised somehow.
Right, something direct.
Exactly. And the critical outcome here is a significant amplitude drop. So a clear reduction in the signal strength, but, and this is key, it's localized. It's only in a specific anatomical region, like, say, the left arm only.
Okay.
And you get an immediate visual cue, too. The affected channels, they flash red on that montage map. Recognizing this specific localized change immediately is, well, it's absolutely vital for patient safety. It lets the team react fast, potentially reverse the issue before any permanent damage occurs.
That's fascinating. So one localized flashing red, and then in contrast, you have the anesthesia event, that's the A button, the syringe.
Right.
This simulates a systemic change, something like a deepening of anesthesia.
Exactly. A whole body effect.
So the effect here is global, right? You'll see maybe a moderate amplitude reduction, the signal gets weaker, and a slight latency increase, meaning the signal takes a bit longer to travel.
Little delay.
But it's across all channels.
That's the key difference.
Yeah.
All
And
channels.
visually, all channels will flash amber, indicating that sort of systemic, maybe less immediately critical effect.
Correct. Amber for global.
So for someone new to this, what's like the most common pitfall when trying to quickly tell the difference between a surgical issue versus an anesthetic effect in the heat of a live procedure?
That's an excellent question because making that distinction quickly, differentiating between that localized surgical issue and the systemic anesthetic effect, it's paramount. It's job number one, really.
Yeah.
The simulation teaches you to avoid the pitfall of, say, overreacting to a global change that looks alarming but is just anesthesia. Instead, it sort of ingrains the pattern recognition. Red flashes mean localized, urgent, possibly surgical. Amber flashes mean global, systemic, likely anesthetic related.
It's training that instant pattern recognition under pressure.
Exactly, training you to spot those distinct patterns, which then guides your immediate response. And of course, once you've run an event and analyzed it, you can always use the recover or reset buttons to get the simulation back to its stable baseline state and then try another scenario.
Okay, so beyond simulating the big events, just mastering the view of the data is key to interpreting it effectively, right?
Oh, absolutely. How you look at it matters.
That's where the display controls come in, specifically gain and sweep. These parameters seem crucial for helping you interpret the data, letting you sort of tailor the display to spot exactly what you need to see.
Definitely. Think of gain like the volume knob on your stereo, but for the height or the strength of that electrical signal,
Okay?
it's measured in microvolts per division, or 1 diff. If you increase the gain, you basically magnify those really low amplitude signals, making even tiny electrical whispers visually larger.
Ah, so you can see faint signals better.
Precisely, which is essential for spotting subtle changes that might otherwise get missed. And conversely, if a signal is like way too strong and it's clipping off the top of the screen,
Right, getting
you
cutoffs.
decrease the gain to bring the whole waveform fully into view so you can analyze its complete shape.
Makes sense. And then you have the sweep control that adjusts the horizontal timescale measured in milliseconds per division, EMS div. This one seems really powerful.
It really is. A faster sweep, which means a lower EMS-div setting, effectively stretches the waveform out horizontally.
Okay, stretches it sideways.
Yeah, it's like hitting the slow motion button on a critical moment in sports? It allows for a much more detailed analysis of the waveform's latency, basically, how long it takes for that signal to travel, and its unique morphology, which is just its shape.
Gotcha. So slow-mo for nerve signals.
Pretty much. These details, the latency and morphology, they can tell you everything about the health and the speed of nerve conduction. It's like analyzing that critical play in slow motion to see exactly what happened. And just quickly, for anyone just getting started or maybe wanting to see the full range of features without clicking around themselves, there's a handy Awk Play demo mode.
Oh, okay.
Yeah, it offers an automated tour of the simulator's capabilities, and it showcases all these functions, the events, gain, sweep, all in action.
Looking ahead a bit then, this simulation feels like more than just a learning tool. It seems like a kind of foundational platform with, well, incredible potential for bridging that gap between education and actual clinical practice.
I agree completely.
It's about taking that simulated muscle memory and making it work in the real world, right?
It absolutely is. And one really powerful potential enhancement would be adding automated measurement cursors.
Okay, what would that do?
Well, this would directly mirror the functionality you find in advanced clinical IONM software that's used in the OR today. Imagine the system automatically placing little cursors on the waveforms to calculate crucial metrics like peak-to-peak amplitude, the full strength of the signal,
Right.
onset latency, the precise timing of when the signal arrives.
So automating the measurements.
Exactly, which raises an important question for us. How much can automation like that effectively aid human interpretation without maybe fundamentally altering or even replacing that core skill of human expertise? It's a balance.
That's a really interesting point. And building on that, another exciting area seems to be advanced artifact simulation.
Oh, yeah, dealing with noise.
Because in the real world, these systems are just bombarded by all sorts of noise, aren't they? Like high-frequency electrical interference from cautery devices surgeons use,
Yeah, the bovie, always a challenge.
or just sporadic motion artifact if the patient moves slightly. And these things can really obscure the important data.
They absolutely can.
So adding these complex, unpredictable noise sources to the simulation would truly test the resilience of a user's interpretation skills, wouldn't it? And their ability to use filtering techniques, just like they'd have to in a live OR.
Definitely. It makes the challenge much more realistic. And then if we connect this to the sort of the bigger picture, machine learning integration, that's where it gets truly transformative, I think.
Okay, AI meets IOM simulation. How?
Well, think about using the simulation to generate a massive labeled data set of all these different INM scenarios. Thousands of examples of normal signals, surgical events, anesthetic phage, maybe even different types of art.
The AI.
Exactly. That really robust data set could then be used to train powerful machine learning models. A model could potentially be trained to automatically classify waveform changes in real time, maybe labeling them as normal, or flagging a potential surgical event, or identifying an anesthetic fade.
Wow.
This provides a foundational platform, really, for a genuine real-time decision support system right there in the operating room.
So like an expert assistant looking over your shoulder.
Sort of, yeah. Such a system could potentially profoundly enhance patient safety by augmenting the human ability to quickly interpret all this complex data, maybe flagging critical changes in an instant, especially when the team is focused on the surgery itself.
This deep dive really underscores the immense power of these high-fidelity simulations like this one for mastering complex critical skills, especially in these high-stakes environments.
Hmm.
It's clearly not just about learning the theory, it's about building that intuitive recognition, fostering real preparation, and achieving a level of precision that, well, it can save lives.
And that really leads to perhaps a provocative thought for you, the listener, to consider how these types of advanced interactive digital tools are maybe not just teaching aids anymore.
Right. More than that.
Yeah, they're becoming foundational platforms for developing the next generation of medical technology itself, including things like AI-driven decision support. And it makes you wonder what other highly specialized fields, maybe complex engineering design or even mission control for space exploration, could be revolutionized by similar high-fidelity, data-rich simulations. Think about the implications for just accelerating expertise and boosting safety across all sorts of critical industries.
It's still working. Claude 3.7 still making changes for us. So stay tuned. Stay tuned. Yes, so everything we do eventually available on BioniChaos.com. So we have neurology, cardio, imaging, vision, hearing, electromyography, EMG. Those being developed in the last 2.5 years. So there's a lot out there. My expertise is in actually hearing cochlear implants and EEG, actually like implantable EEG, but we don't talk about it. Well, mainly because it's gory. And this is TMS simulation, and you can select your coil type, circular or figure eight. Figure eight is standard. Then you can generate your simulation of the brain. You can target specific areas. This is just a simulation, of course, yeah. So we'll be happy to improve it based on your feedback. Yeah, you can select the coil, location, amplitude, stuff like that. Claude Sonnet 3.7 stuffed things up. Luckily we have a copy. Yeah, so that's what we had before. Now we're trying to improve it, but we are getting errors. Some missing events. Can we see something? No waveforms. No waveforms. Where are my waveforms? Any other potential issues to fix? Well, I have to let it run stuff in the terminal. Hey, can you fix this and any other errors we might be having in the code? Currently the waveforms are not showing. blame, say, Claude 3.7 for stuffing up my code. Luckily we have the previous copy, so yeah, we might continue from the previously saved version at another time. So I'll see you next time. Don't forget to check the website, leave your comments, likes, subscribes, check Patreon as well. And I'll see you next time. Bye.